Good morning. Welcome you all to today's GATE coaching class. Myself Valarmathi, Assistant Professor, Department of Information Technology in S.A. Engineering College. Today GATE topic is minimum spanning tree in algorithms. Before that, we will see about the agenda of this today's topic, the basic idea behind the minimum spanning tree, and then what is spanning tree, and then minimum spanning tree, the algorithms which is used in minimum spanning tree, applications of the real-time applications of minimum spanning tree, previous year GATE questions, and then conclusions. First we will see what is graph and then tree. A tree is an undirected graph. It contains a collection of vertices which are connected by the edges, but it will not form any cycle. We can say it as a tree. What is a graph? A graph is a collection of vertices which are connected with the edges. It may be a directed edges or undirected edges, but also it may be weighted or unweighted. It may form these cycles. So, see here I given an example for the tree and the graph. Every tree is a graph, but all the graph is not a tree. See here, the nodes A, B, C, D, E or the vertices, or we can say it as a node, which are connected with the edges. While connecting these edges, it forms a cycle. So we can say this as a graph, but it is not a tree. Here, the vertices A, B, C, D, E are connected, but there is no cyclic formation. So we say this is a graph as well as a tree. Let's see what is spanning tree. Spanning tree is nothing but a tree that is a subgraph of the graph. From this subgraph, we will be getting the subgraph, which is a tree. It should not form any cycle. In the spanning tree, we have few conditions. One is a tree should contain all the vertices of the tree. That is, whatever the vertices which is present in the graph, it should be present in the tree. And also, it contains the number of vertices. Based on the number of vertices, it should contain the edges. If it has n vertices, it should contain n minus 1 edges. Next thing, in this tree, it should not form a cycle. That is, no edges traverse twice. Let's see an example. This I given a vertices A, B, C. For this tree, I am getting 3 spanning trees. That is A to B, B to C, or else A to C, A to B, A to C or C to B. These 3 are the spanning tree of this graph. This graph is this tree is the subgraph of the graph. You can also say it as a tree or a graph, but it does not form any cycle. What is that minimum spanning tree? In this previous slide, we see about the spanning tree. From the spanning tree, which tree have to choose? That is based on the minimum cost. Which cost the minimum cost? Based on the cost, we will choose the minimum spanning tree. Minimum spanning tree is also said to be a minimum weighted spanning tree or also minimum cost spanning tree. In this, it may contain the edges of undirected weighted graph. This minimum possible total edge weights we will find out. Based on this weight, we will say this graph is the minimum spanning tree. So it will be used in the real world examples of identifying the traffic distances and then traffic load, conjunctions and many arbitrary values. Let's see an example of minimum spanning tree. In this, I use the 4 nodes A, B, C and the D, which are connected with the edges, and also it is mentioned with the weights 5, 5, 2, 1, 4. In this, we have to say first condition is it should contains all the vertices. That is A, B, C and D. All the vertices should be present in our tree. And also there is no cyclic formations. This is the third point. Second point is it should contains the wedges. Edges should be number of vertices minus 1. That is, it contains 4 vertices means it contains at least at most, that is, it should contains 3 edges. A to B 5, B to D 2, D to C 4. Then A to B 5, A to D 5, then D to C 4. A to B 5, B to C 1, C to D 4. Then A to D 5, D to B 2, B to C 1. These are the 4 possibilities. The minimum value for this tree is 5 plus 2 plus 4 is 11. For this tree is 5 plus 5 plus 4 is equal to 14. On this tree is 5 plus 1 plus 1 4 equal to 10. For this tree is 2 plus 5 plus 1 is 8. Compared to these spanning tree, which one is minimum is last spanning tree is the minimum. So finding the minimum spanning tree is 2 plus 5 plus 1 is 8. Next we will see about the algorithms which is used in minimum spanning tree. The 2 algorithms we used in Kruskal algorithm and then Prim's algorithm. We can say this as a greedy algorithm. Let's see Prim's algorithm. Prim's algorithm, in this it follows these certain steps. That is, it contains all the edges in the graph. It should be the minimum spanning tree. And this first they start with any of the vertices to obtain the minimum spanning tree, and then select the minimum cost of the edges and add that edges. If it is not a former cycle, add that edges in the cycle. If it forms, means then we can discard that edges. Repeat step until all the vertices are visited, because in minimum spanning tree first conditions it should contain all the vertices. Till it reaches all the vertices, we have to find the steps. Consider, I am taking the here example 6, 1, 2, 7, 5, 4, 3. These vertices are connected with the edges. It contains some values. It can take as a distance or any other values. In this, first I am taking as a node 1. From this node 1, it may go to node 6 or node 2. But the least value is 1 to 6. So I am choosing node 1 to 6 is 10. And then next step, I am chosen from 1 to 6 they already visited. From 6 it can have only one path, 6 to 5. That is 25. Next I move from 5. In the 5 it has the two paths, 24 and then 22. Compared to 24 and 22, 22 is lesser. So I move to 22. That is node 4. At next from node 4, I can go with node 7 or node 3. Based on this value, node 3 is lesser value. So I move to from 4, 3, 2. From 3, there is no other options. I can move only to node 2. So I moved. So next from node 2, I can go to node 1 or node 7. But I will choose node 7 because of lesser value, and also if I choose node 1, it will contain as a loop. So definitely I will not choose the edges. It will discard the edges. So I move from 2 to 7. This is the spanning tree of this algorithm using Prim's algorithm. Next thing is the Kruskal algorithm. It is similar to the Prim's algorithm, but here we'll choose the edges based on the values, that is which contains the lowest value. Based on these values, we'll choose the edges which are going to perform, which is also called as the minimum forest spanning forest. How it works means it starts the edges in the graph from the lowest to the highest. First is choose with the lowest value, then it moves on to the highest value. And also this process is repeated until all the vertices are visited, and also while choosing this path, if any vertices forms a cycle or loop, it will discard that. Let's see an example. Consider this example, node A, B, C, D, E, F, G, H, I. These are connected with the edges with some values. So in this graph, first I have to choose the node which contains the least value. For example, from B to D, it contains a value as 1. So I will go with this. First I will choose the B to D. Next I will move from G to H. I can choose anything first, G to H or B to D. Both are contains the same value. I visited as G to H. Next I will move on to 2, D to E and then B to C. I visit the D to E and then B to C. Next I will check the E to, third value is E to G and then G to I. So I move to E to G. See here I am choosing D to I. Already I visited G to H and then H to I. These nodes are connected. If I choose D to I, it will form a loop. So I will not choose this edges. So I will discard this edges because it will not form a tree. Next thing I will go with the 4. See here I will choose A to C. Next I will go for C to D. I will not choose C to D because if I choose C to D, it will discard that path. It will form a loop. So I will not choose C to D. Next, see all the vertices are connected. There is no other path to choose the vertices. Okay. This is the Kruskal algorithm of obtaining. This is a subgraph of the graph which contains all the vertices, and also there is no loop formations done. Next we'll see about the applications where and all we are using this minimum spanning tree. This minimum spanning tree is used in telecommunications network. For our example, considering the cable length, how much of length is the minimum of finding the length, and also the railway tracks to identify cover all the distances with the minimum amount of space. And also electric power grids efficiency, distribute the electricity across regions, water supply systems, optimize the pipe layouts for cost-effective distributions, road network planning, minimizes the construction cost while maximizing accessibility, Local area networks, LANs, connects the device within a limited area. Wide area networks link geographical dispersed locations. And also in the circuit board designs, routes the electrical connections, minimizing the wire length and the inference. Let's see with the previous year gate questions. First we'll go with the first question as the number of distinct minimum spanning tree for the weighted graph below is. The graph is given, which is in the form of the hexagon and the triangle. In this graph, the value is given with a weighted graph. First go with this triangle. In this triangle we have the values, minimum value is 1, and then next move with the hexagon. In this we have the minimum value is 1 1. First I will visit 1 and then 1 1, these 1 vertices, these 1 edges. All these edges are visited. Afterwards remaining I have 2 vertices, 2 2. If I visit any one of these vertices, if I visit 2 vertices, it will form a loop, so I should visit any one of these vertices. So I can return as 2C1. This is permutation combination. From this I will not visit these vertices, it will form a loop. Similarly, I should not visit these vertices also, it can also form a loop. So I will discard these vertices, edges. And this next you see, I can visit any one of these 3 edges, then only I can form it as in a tree. So you can say 3C1. So the answer is 2 into 3, will get the 6. The option are given as 6, 9, 14, 19. The answer is 6. Next we'll want next questions. In this question they given as a vertices and edges are connected, and also they given as a weighted. This is a weighted graph. In this weighted graph they given which one of the following is not the sequence of edges added to the minimum spanning tree using Kruskal's algorithm. So using Kruskal's algorithm, first we have to go with the least value. So in this graph, first least value which contains in the node B to E. First we have to check where the B to E is. B to E. First we will visit B to E. See, all the options are given with B to E. Next we will visit the node with the least value, that is 3. We can visit E to F or A to C. The options E to F, A to C, E to F, A to C, A to C or E to F. Listen here, E to F, B to C is given. So B to C, the value B to C is 4. We will not visit this. So the wrong option is the B to E, E to F, B to C, A to C, BF to GF. This is not the sequence of the Kruskal's algorithm. Next questions. The graph shown below has 8 edges with distinct integer edges weight A. Minimum spanning tree emerged. That is, minimum spanning tree is given, is of weight 36 and contains the edges AC. That is, the edges AC is given. Minimum spanning tree BC, DE, EF and then DF. The given edges is A to C and then C to B, B to E and then E to F and then F to D. This is the minimum spanning tree. In this spanning tree they given the value as 36. For this we have to calculate whose the edges of minimum spanning tree in the graph, which is the minimum possible sum of the weights of all the 8 edges of the graph. We have to, if you add A, C, D, E, F, C, all the values, if you add all the values of the edges, we have to get what is the output of this answer. This one, if it is taken as a minimum, it should be greater than this. So we can take it as a 10. If it is greater than this, we can say it as a 16. They said if it is greater than this, we can take it as a 7. Already 4, 6, we can take it as a 7 from this. So if you add all the values, 9 plus 10, 15 plus 2, 16 plus 7, 7 plus 4 plus 6, we'll get the answer as a 69. We'll move on to the next question. 4. Let G be a connected undirected graph of 100 vertices and 300 edges. They given us a 100 vertices. 100 vertices means it contains 99 edges. and 300 edges. For 300 edges, we have to calculate the weight of the minimum spanning tree of G is 500. The minimum spanning tree weight is given as 500. When the weight of each node of G is increased by 5, for every node the weight is increased by 5. So what is the weight of the minimum spanning tree? For first node to the last node 100, I am taking as the 99 edges. For every node it gets increment by 5. So at last we are calculate the minimum spanning tree value is given as 50. 500 plus 99 into 5, at last we'll get 995. The option B is the answer. Next, move on to the question number 5. The number of distinct minimum weight spanning trees of the following graph is. It is similar to the first questions. It is the how to find the possibility of combinations. How many possibilities of to obtain the minimum spanning tree. And the C. First, we'll take the least value. Least value means the value which node which contains the vertices which contains the less value, that is 1, 1, 1, 1. These are all the vertices we have to visit. Next, we will visit the vertices 2. From these 3, we can visit any one of the vertices, otherwise it will form a loop. From these 3 also, we can visit any one of the vertices, otherwise it also forms a loop. From this I can say it as 3C1. From these 3 I have to visit 1, and then from these 3 I can visit 1. So it is 3 into 3, 9. I will not visit this node 3, 3 because if I visit this it will form a loop. I will discard this node. I have given in the diagram, see, I visit the node A to B and then A to F, similarly D to E and then D to C. See here I am discarding the node 3 because if I visit this node it will form as a loop. Next thing, I can visit any one of these 3 to achieve the tree, to visit to connect the B and the G, or else A to G, or else F to G. But also similarly in this side I have to connect any one of these edges, C to G or G to D, or similar G to E, or any one we can choose. So it can represent as 3 into 3, 9. Now the conclusion of this topic is more efficient for a real-time examples, that is connecting everything at the lowest possible cost. It will be using in the clustering data, label cables, and also building roads, designing circuits. It is the fundamental for most of the transportations. It is used in many real-time applications. Thank you all. We'll meet in the next section. Thank you so much.